Newton's first law, the law of inertia, one of the ways to state it is that if objects are moving at a certain velocity, they'll maintain that velocity unless acted on by an external force. Objects will only accelerate if acted on by an external force. So in the case we just went over, where we had the neutral rod, we were pushing it at a constant force, let's say. It's accelerating because of our force, but then as it got closer to this negatively charged rod, it started accelerating faster. There must be some other force present now other than us pushing it. We call this force the electric force. And as with all forces, it is measured in newtons. In the late 18th century, Joseph Priestley reasoned and John Robeson measured that the force between two objects followed the same principles as the gravitational force, and that the force between two charged objects depends on the inverse square of the distance between them. So this electrical force is proportional to 1 over r squared. I underline these words. Both are absolutely mandatory for doing physics. Reasoning is where you come up with some new ways of looking at the universe based on previous experiments, previous observations, current observations. That's wonderful, but until you can measure it and prove that it works, you have nothing. And on the other hand, if all you're doing is measuring, you might never come up with fantastic breakthroughs that are not obvious from the measurements. For example, Einstein, Faraday. So both of these are key parts of physics. Then in 1785, Charles Coulomb published a paper, also a key part of physics and science, so other people can read what you did and then try your experiments. This was based on very detailed experiments, and it definitively proved Priestley and Robeson's work. He also showed that the force was directly proportional to the size of the charges. What's really cool here is he used a torsion balance to do this, and that was based on the same principle that Henry Cavendish used to measure the gravitational constant. And here we have it. This is Coulomb's law. The magnitude of the electrical force, see I have no vector here, I'm just looking for the size, is equal to K times the absolute value of one charge, absolute value of the other, divided by the distance between them. See the little subscript here, 1, 2? That just means the distance between charges 1 and 2. Don't automatically think it's a radius. Sure, that's what you learned in math, but in this case, r can just mean the distance between two things. K is the Coulomb constant, and it equals 9.0 times 10 to the 9th Newton meter squared per Coulomb squared. Q1, absolute value of the net charge on one object. Q2, absolute value of the net charge on the other object. R1 and 2, the distance between the two objects if they are point charges. Now, if they are spherical or have a shape, it's the distance between the centers of the objects. Please note the striking mathematical similarity to Newton's law of universal gravitation. Coulomb's law is used to calculate the magnitude of the electrical force. Each object exerts the same force on the other, except in opposite directions. Newton's third law applies to all forces, not just mechanical ones, although very soon we're going to talk about those mechanical forces and their relationship to electrical forces. Since electric force, like all forces, is a vector, you need to specify the direction of the force whose magnitude was determined by Coulomb's law. This is done by examining the signs of both charges and remembering that like charges repel and opposite charges attract. As mentioned a little earlier, both the electric force and the gravitational force are expressed using a similar mathematical formula where the magnitude of the force decreases as 1 over r squared. However, a couple differences. Electric force can be attractive or repulsive. Like charges repel, opposite charges attract. Gravitational force is always attractive. The electric force is on the order of 10 to the 36th times stronger than the gravitational force. We made that point earlier when we rubbed the plastic ruler with fur and we were able to lift up bits of paper, fighting the entire Earth who was trying to keep the paper down. The dynamics unit of this course covered the contact forces. Remember the normal force, tension, friction? Newton's third law applied to them, as it also applies to the electrical force. Is there a deeper connection between the electric and the contact forces? Within your group, or by yourself if you're at home, think about or discuss what you think what this connection could be. And here's our hint. What are cars, baseballs, water, people, anything you can see? What are they made of? All of the objects that were referenced on the last slide are made up of atoms. Atoms, as we saw earlier, have a positive nucleus deep within the atom, surrounded by a cloud, that's one way of talking about it, of negative electrons. The predominant force acting between atoms is the electric force. The positive charges are way deep, but the electrons between objects are interacting all the time, and they're repelling each other. Later on, we're going to see how this electric force is really part of something called an electromagnetic force, but that's a little later on. So at this macro level, the predominant force is the electric force, which is a repelling force between the electrons of different atoms. We don't want to talk about the interactions between individual atoms because there are just so many. It's incomprehensible how many atoms make you up. So we will describe these interactions, which are based on the electric force, as contact forces. These are non-fundamental forces. The fundamental forces are electromagnetism, gravity, strong nuclear, and weak nuclear. But we're going to look at this macro view of the electric force, and we're going to call them contact forces, and they are the normal force, tension force, and friction. A quick summary. Normal, tension, and friction forces are called contact forces. Why are they contact forces? They involve objects touching each other. The source of the contact force is the electric force. It's the electrons surrounding the nuclei in the objects that are touching each other that repel each other. That is the contact force, and its source is the electric force.